Hi, in this lecture we are going to look at local extremes or local extrema of functions of several variables. If you recall what we did, this is it's similar to the parts of application to differentiation, where we looked at a critical value, and from the critical value we were able to get or deduce whether the function has a local minimum or a local maximum. So that is exactly what we are going to do here. Although we will not extend the knowledge that we learn here to sketching functions of several variables, but the idea is roughly the same. So let us start off by defining a critical point of functions of several variables. But before we get to the definition of a critical value of a function of several variables, let us look at the definition of a function of a single variable. So what we did is that a point C is called a critical point of the function f of x if you take the derivative and set it equal to 0, or the derivative does not exist. This is what happened in one variable. Now, what happens in two variables? So here we do not have a point C. We have an ordered pair, which is considered as a point in functions of several variables, AB. So we call it a critical point or a stationary point of f if, remember that this is a function of several variables, so it does not have one derivative, but it has two derivatives: the partial derivative with respect to x and the partial derivative with respect to y. Right, and here it's actually at the point C. Right, then or if one of these partial derivatives does not exist. So you know how that case holds, okay? How do we deduce that the derivative does not exist? The idea is still the same. So let us recall something with a critical point. We learned that a critical point is what we were able to actually classify when we did the first derivative or the second derivative test, meaning that a critical point or at a critical point, a function could have a local minimum, a local maximum, or neither of the two. Okay, so let us see how then do we find a stationary point of a function of several variables. So find the stationary point or points of f of x, y, which is x squared plus y squared minus 2x minus 6y plus 14. What does the definition say? The definition says that I should find the derivative, the partial derivative with respect to x and the partial derivative with respect to y, and set these derivatives equal to 0. And whatever I get there is going to give me a pair, an ordered pair, AB. Okay, so let's see. So let's find the first derivative, which is the partial derivative with respect to x of xy. This is equal to 2x. This one is 0 minus 2, right? Minus 0 plus 0. So this is 2x minus 2. And then what do we do with the derivative? We are going to set it equal to 0. Right, so if we set this derivative equal to 0, then we get that 2x minus 2 is equal to 0, which means that 2x is 2, so therefore x is equal to 1. Now let us find the partial derivative with respect to y of xy. Then if we differentiate with respect to y, partially with respect to y, then we have 2y minus 6. And the definition says I'm supposed to equate this equal to 0. So 2y is equal to 6, so y is equal to 3. So therefore, the only stationary point or critical point is 1, 3. Remember that this is evaluated at xy. It is not the value. So if we were to compare it with the language that we used in single variables, then we would say that it has a critical point at 1, 3. Okay, so then the value is f evaluated at 1, 3, which you can plug in the formula. Right, the next one. Determine the critical point or points of the following function once again. So what do? We first find the derivative with respect to x, the partial derivative with respect to x of xy. So this one is 4x cubed minus 4y. And we must find fy partial y, which is equal to, it is also 4y cubed minus 4x. So in order to find the stationary or critical point, we are supposed to set these derivatives equal to 0, meaning that f partial x or subscript x of fy equal to 0 means that 4x cubed minus 4y is equal to 0. And remember that the definition has and 4y cubed minus 4x is equal to 0. Okay, so I'm going to solve for one of them. This one I'm going to divide throughout by 4, and I get x cubed minus y is equal to 0. And this side I have y cubed minus x is equal to 0. Then this is the same as y is equal to x cubed. And I'm going to call it equation 1, and I will call that one equation 2. So now we have to solve simultaneously and find the values of xy. Those values of xy will be giving us the critical values. Okay, so how am I going to do that? So I am going to substitute equation 1 into equation 2. And this is what I get. So equation 1 says y is equal to x cubed. And equation 2 has y cubed minus x. So it means that wherever I see a y, I'm going to plug in x cubed. Cubed minus x is equal to 0. So remember the law. In this case, ab to the power c is the same as a exponent bc, which means that I have x to the power 9 minus x is equal to 0. So now I have to solve this equation. So what does this mean? I'm going to first factorize x. I'll be left with x to the power 8 minus 1, which is equal to 0. This is a difference of 2 squares. If I have x to the power 4 minus 1 times x to the 4 plus 1 equal to 0. Once again, this is another difference of 2 squares, which means that I have x of x squared minus 1, x squared plus 1, x to the power 4 plus 1 equal to 0. Then this again is a difference of 2 squares, which means that I have x minus 1, x plus 1, x squared plus 1, and x to the 4 plus 1 equal to 0. So what does this mean then? Remember that from here, it means that x is equal to 0, or x minus 1 is equal to 0, or x plus 1 is equal to 0, or x squared plus 1 is equal to 0, or x to the power 4 plus 1 is equal to 0. All right, but we know something. We know that x squared plus 1 equal to 0 and x to the 4 plus 1 equal to 0, their solutions lie on the complex plane. And we are not trying to sketch solutions or functions or graphs of functions in the complex plane. So therefore, we consider this one and this one as, so I'm going to write here that the solution is in the complex plane. Remember that that's the C that we write. So therefore, no solution. Remember that you have to conclude. So the fact that I'm saying that the solution is in the complex plane, it is me saying that I already have some knowledge about complex numbers. And I know that this is definitely not what we are trying to sketch, okay? But you are supposed to clearly, or you're supposed to make it clear that we do not have a solution in this case. So then what does it mean? It means that x is equal to 0, or x is equal to 1, or x is equal to minus 1. Right. So then what are then the associated y values, okay? And the associated, right, y values are, so it's up to you whether to find the y value, you substitute in equation 1 or in equation 2. But because I have the x values already, I'm just going to substitute in equation 1 because it says y is equal to x cubed, okay? So y is equal to 0 cubed, so then that gives me 0. And then the next value is minus 1 cubed, that gives minus 1. And the next value is 1 cubed, which gives 1. So therefore, the critical points are 0, 0, minus 1, minus 1, and 1, 1. Okay, so you see that if you are finding a critical point, let us compare the two examples. For the first one, we saw that if we take the partial derivative with respect to x, we ended up getting a solution that was x is equal to. And when we took the partial derivative with respect to y, we got something that said y is equal to something, right? But then equation 2, the next example, which was example 2, showed that we are actually trying to solve this simultaneously. So in the test or exam situation, you should expect either or, okay? So now, remember that what I have said here in red is that at a critical point, a function could have either a local minimum, a local maximum, or neither, okay? But we do not get into too much detail of how to find the absolute minimum and absolute maximum and those other properties of f that we have done for single variables. Okay, however, we do or we can classify a critical value or a critical point and deduce whether the function has local extreme or extrema at the critical point. Okay, so what does it tell us? We have something that we call the second derivatives test. Okay, not second derivative. We use second derivatives. There are many of them that we will use. Okay, so the test here, unfortunately, we do not have the first one in this case. So it's like you are forced to do this one, okay? So suppose the second partial derivatives of f are continuous on a disk with a center AB. So basically what that says is that the partial derivatives are continuous in the domain, okay? And suppose that if x is equal to 0 and if partial x or subscript x at a, b is 0 and y is 0, what does this mean? Look at the definition one that I have given you. It means that AB is a critical or a stationary point of F. That is what we have to classify. So then let D be equal to, you need to know this formula even off by heart, okay? D is the second partial derivative of x, so it's xx at the critical point, multiplied by the partial derivative of y partial, so then it's the squared derivative or the second derivatives of y, and then minus the derivative squared. Okay, the mixed derivatives. So we say that if you calculate this expression d, right, and you substitute in, so let us look, what does it mean? It means that I have to find, so I have a function f of xy. I have to find f of x and I have to find f of y. And then I have to find f of xx and f of yy and f of xy. Not of, but then they're partial derivatives. And then I have to evaluate the derivatives at the critical values, right? And after I find the derivative at the critical value, the value that I am going to get after I do this expression here, if it's positive, and this value here, xx, at the critical value is also positive, then f at AB is a local minimum value, or f has a local minimum at AB. So if it is again positive, but then the second derivatives of x are negative, then f at AB has a local maximum and f at AB is a local maximum value. Right. And then if you calculate this value and you get that D is negative, then F is not a local minimum or a local maximum. And what I have written in red is that at that point, then it is called a saddle point. So a saddle is usually what is put on the horse. So if we were sketching these functions, you would realize that at this specific value, it looks like a saddle, what you put on the horse and sit on it, okay? So we can also deduce that if D is equal to 0, then the test is inconclusive. So we cannot conclude anything about the test. Right, so classify the critical points of the function. F of xy is x to the power 4 plus y to the power 4 minus 4xy plus 1. Okay, so this is the one that we did here. So we have found the critical points. Now we have to classify the critical points, okay? So what you are supposed to do, if you weren't asked to find the critical points first, you would have to calculate the critical values first and then classify them. So I'm going to write here that the critical points which we obtained from example 2, they are 0, 0, minus 1, minus 1, and 1, 1. Okay? Then, now let us find and classify. Okay, so now we have found the critical points. Now let us classify them. First things first, we write down the formula. What does the formula of the second derivatives say? It says that d at AB, which is the critical value, is equal to fxx at AB multiplied by fyy at AB minus fxy, the mixed derivative, at AB, everything squared. So what does this mean? It means that I need to find the derivatives. So we already have that the first derivative with respect to x is 4x cubed minus 4y. And then the partial derivative with respect to y is 4y cubed minus 4x. Now let us find the second partial derivative at xy. Then it is 12x squared, right? That's what we have. And fyy means that we are taking the partial derivative. Remember that if you cannot remember what we are doing here, you put brackets here. Then we are taking the partial derivative with respect to y of what has already been differentiated with respect to y, which means that you are taking the partial derivative with respect to y of 4y cubed minus 4x. And then the answer is 12y squared minus 0. Okay, and then what do we need? We also need another derivative, which is fxy. And how do we calculate this derivative? Remember, once again, you can put the brackets. It means that you are taking the partial derivative with respect to y of what has already been differentiated with respect to x. So it means that we are taking the partial derivative with respect to y of 4x cubed minus 4y. Okay, so then what is the answer here? With respect to y, the answer is minus 4. But then you can see here that these are continuous functions. Polynomials are continuous functions. So therefore, it doesn't matter whether you calculate fxy or fyx. Okay, so with the mixed derivative, it doesn't matter by Clairaut's theorem, right? So now what does this mean in terms of our equation, or in terms of the second derivative test? So therefore, we have that dxy. I'm not going to use a and b. It's xy because those are the values that we have. It's at xy instead of ab. fyy at xy minus fxy, all of it squared. Now, what is the partial derivative with respect to x? With the second derivative with respect to x, it is 12x squared. And then the y, and then the second one with respect to y, it's 12y squared, right? Minus this one is minus 4, all of it squared. So from here you can already substitute, but then since this is simple, I can continue and say this is 144 x squared y squared minus 16. So you don't need to necessarily put in this step. This one is sufficient, okay, because you can already substitute in there. Now we get to the important part. Now let us classify. What is d at 0, 0? So that is my critical value. d00 means I'm going to say 144 0 squared. I substitute here 0 squared minus 16, and then this gives negative 16, and negative 16 is less than 0, right? So let's go. What does the test say? We are here. D is less than 0. So this means that f is not a local. Then it means that 0, 0 is not a local minimum or a local maximum. And then what is written in red is that that point, which is 0, 0, is called a saddle point because of the fact that when we calculated d, we got a negative value. So therefore, by the second derivatives test, 0, 0 is a saddle point. Right. Let's just create some space here. Okay. Then another one. We are not done. We need to find the next value. What was our other critical value? It was -1, -1. So we go d -1, -1. Then we substitute -1, -1 there. So we have 144 minus 1 squared minus 1 squared minus 16. So you plug this in your calculator and it should give you 128. 128 is positive, okay? So let's go back to the test. So we have that 128 is positive, which means that I am between A and B. Oh, then what does it mean? It means that I have to look at something else. There's an and. So now I have to look at fxx. Okay, so then the second derivative evaluated at -1, -1. And if it's positive, then I'll have a local minimum. And if it's negative, then I'll have a local maximum. Right, so let's see. So fxx at -1, -1, what is that second derivative? It's this one, right? It's 12x squared. So it means that whenever I see an x, I put in -1. And wherever I see a y, I put in -1. And this gives me 12, which is positive. So I have that d is greater than 0, and the second derivative is also greater than 0. So what does it mean? Therefore, by the second derivatives test, -1, -1 is a what? What is it? So both of them are positive. It's a local minimum. Is a local min. Right. Or if you want, you can say at -1, -1, f has a local minimum. Okay? And what else can we conclude? If we calculate f at -1, -1, so this means that you are supposed to substitute -1, -1 here. You will get that the answer is equal to -1. So then this is what we call a local minimum value. Remember, that's the value. Right. Then we now have to do D11. If we do D11, once again we substitute 144, 1 squared minus 16, and then this gives another 128, which is positive. So remember then that it means that we have two cases. So we have to calculate fxx at 1, 1, and then that is 12 at 1 squared, which is 12, and that is positive. So once again, by the second derivative test, 1, 1 is a local minimum as well. And f11, which is equal to, so if you plug in 1, 1, you get the same value at -1, and that is the local minimum value. Okay. The language is important here. Right. And then the last one, suppose 1, 1 is a critical point of the function f with a continuous second derivatives. If xx and xy, and fyy are those given values, what can be said about f? You know that these are my type of questions that I like asking. So this one I'm testing your understanding. So what do we do here? You are supposed to calculate d at xy, okay? Which is, you first write down the formula. So it's fxx xy times fyy xy minus the mixed derivative at xy, all of it squared. And then you find d11. d11, it means that you have fxx at 1, 1 times fyy at 1, 1 minus fxy at 1, 1, all of it squared. Okay, so then this is equal to, now you use the formula, look at what's given. This is 4 multiplied by 2 minus 1 squared. So that's 8 minus 1, which is 7. Right. That's what we have. So we have that since this, remember, is positive, d11, which is equal to 7, is positive, and we have fxx at 1, 1. This one is equal to 4. That is also positive. So then what does the second derivatives test say? So you realize that the second derivatives test tell us that 1, 1 is a local minimum. So you can write it as, therefore, f has a local minimum at 1, 1 by the second derivatives test. Okay, now try it out. What happens if I change this value here to be equal to minus 4? Okay, see what you can get. Okay, try that out for homework. And now you should be able, on the notes, to do exercise 3.3 and 3.4. Thank you.